a timeline of our project. Now I'm going to talk about the proof of concept. We started this project in 1998, and during the following 2 years, we tried to build a vehicle using free height magnets, and it didn't work. We didn't have enough magnetic field for the permanent magnetic area. And you can see the cryostat is levitated, the vehicle is levitated. This is the drive, the module, and this is our linear induction motor. It's possible to see the gap right now, that the linear motor. This is the primary and secondary inside the vehicle, and it's possible to see the operation of the vehicle. There is another video here with our group. I'm here. I'm Professor Apolinario, Professor Stefan, and we are levitating inside the model, and we have in this prototype this thing here to feed the vehicle during the operation. Let's talk about the what is that? Yeah, no, it's all right. This is the future invitation to give a talk at a workshop about which I'm not, the subject of which I'm not very familiar with. This is a workshop mainly on superconductivity, and my first warning to you is that there will be a talk not on superconductivity, but rather on turbulence, so on fluid turbulence. So it might seem a very far off subject to speak on this to this audience, but that was the closest I had to superconductivity, and you see that there is indeed a connection in terms, so that some things that we learn about the statistics of fluctuation in turbulence, the loss fluctuation in a turbulent flow, might help us to understand some aspects of flux avalanches in superconductor. A particular type of avalanche that I'll be talking about is quasi-1D systems that the Oslo group has so-called the statistical equilibrium of multi-scale systems. Systems when you have more than one time and length scale. So that that plays an important role, the presence of such multi-scales, and from the presence of those multi-scales implies, as you see, a departure from what we call the canonical formula, the canonical distribution proposed by Gibbs based on previous work of Boston and everything. So the goal here is just to put things in context, give a very brief overview of what the canonical formalism is in equilibrium statistical mechanics, to understand where it may fail, in which circumstances it should be valid, and in which circumstances it should not.
I use that local-density approximation. That's the reason why I don't get good result here. But if you go here, alpha even larger, like alpha 10 power 4 and so on, or 10 power 3, I also do not get good results. And the reason that is that it's strongly spinning, and then the position of particles are important, right? So then I should use not that phi from the continuous model, but something better, right? That's when you enter the Madelung energy now. That is not this. I don't talk up to now, right? So this is the correct, it's a better fit than the previous one, because I'm really considering the position, but it is still a closed form expression, right? So how do we get this closed form expression? Because if you see the phi of x would be a sum right? Of infinite terms. And here we get something that's a closed form expression. How do we get that? So, how do we obtain a closed form expression for the Madelung energy of a lattice? Okay, so that's a regular lattice, right? That triangular lattice. You have here the interparticle distance is x, and here this distance between two rows are I call h. Okay, and h by simple trigonometry I can obtain that. Okay. Well, to calculate exactly the Madelung energy, in this point, for example, I have to sum up all the lattices from here up to infinite and so on, right? So once more, by using trigonometry, I obtain this expression here, okay? And depends only on two numbers, two integer numbers, n and n, right? Then I have this expression. So what I will in the following show is a way to obtain an closed form expression for this quantity, and I will compare with this quantity. So that's the way to obtain a closed form expression for the Madelung energy. I will discretize my triangular lattice. This is a part of the triangular lattice where I want to calculate the Madelung energy at this center point, right? So what is the Madelung energy? Is the energy due to the all particles in this point, for example. Okay? And I will discretize that in several rings, several annulies. The first one, the second one, the third one, right? But remember, that's a continuous. I would think, in principle, that it's a continuous model, so has a density. And I will calculate the charge due to the density in this annuli, and I will put all the charge in the ring, where the ring is in the center. Right? That's like a receipt. Okay? There is a physics behind that I can explain later. So then I have several annulis. I have the Rn. Okay, the n-asimal ring. So that's this ring is x plus 2ny, where this y is the half of the distance of one annuli. And then, for example, if I have here this n-asimal annuli, so it has radius x 2 times n minus 1 y. Okay? So I can enumerate all of them. So the area of one annuli is given by this expression here. So you have, for example, this one an. So suppose that the n is this one. Okay? So you have the maximum radius, that's Rn plus the lowest order, that's this one here, is Rn minus, and you have this expression, this number here, that's just the perimeter of these radius. Okay? So if I sum up all those things, right, and multiply by the
this is the outline, the geophysics concepts, and the very useful to talk about. First, so that there is an analogy that is useful to understand the speaker. Then I'm going to speak about some phenomena discovered in the last 5-8 years. And finally, I'm going to describe it briefly. A few experiments I have done in our department. So as you all know, the metal, only electron is responsible for the electric currents. And in semiconductors, the currents is due to both electrons and holes. They move in opposite directions. under the action of the electric field. Since they have opposite charge, the current ebb. As I said, this is useful to understand the idea of the spin current. And the charge current density that is related to the gradient of the potential, means of the potential. In the Hall effect in a semiconductor, under the action of an electric field, will be such that electrons will be deflected by on the magnetic resistance, diamagnetic resistance, was important for keeping the capacity of hard disk drives increasing with time, as shown here by this already a little old information from my end. It keeps going up. Of course, the steep rise is not only due to the big head, it's also due partially to the improvement in the recording materials. And as you know, Albert Ferg and Peter Newton, who discovered the GMR in 1989, received the Nobel Prize in 2007. Well, let's see how one can generate a polarized current. If we have an unpolarized current, the electrons moving to the right, we have here two spins up and two spins down. Since the collision with the magnetization arc has a larger cross section for spin down, eventually we have larger probability of this electron being reflected. Of course, some will pass through. But this constitutes a spin filter. The electron current on the other side will have more spins up than down, and this is a spin polarized charge current. In 1996, Gonçalves and Berger made a theoretical prediction. It took a few years until that prediction was verified experimentally. They said the following: if you have a spin polarized current, electrons going in this direction, we are assuming that this is a ferromagnetic layer. The magnetization is in this direction, and it polarizes the electrons in the same direction. This is a normal metal, and that's another ferromagnetic layer, which is magnetized in the vertical direction. So electrons will go through, and when they reach this other layer, that's actually a very simple and good explanation of this phenomenon. One electron has to go out for charge cancellation, but the effect of the spin is that there will be a change in the spin, delta S2, which is 1/2 of electron angular momentum. And if we have a certain number of electrons of the spin line. Well, let's come back to the spin current. This is a very good illustration of a charge current. Electrons move in the same direction. With the spins in the opposite direction, we have charge current or no spin current. However, if we have electrons moving in opposite direction, if we have opposite spins, then we have a net spin current with spin up in the direction. Or we could also choose a net spin current with spins down in this direction. So this is a pure spin current with no charge current. The net charge current is 0. And this spin current can also produce, well, that's a problem with my animation. The spin current will produce a torque. So there are other many means to produce torques and to act on the spin. Well, the properties of the electron spins and two important consequences